take somebody down if I never made a sound again. In your eyes, you've already spent my thighs, and you're rocking to the next big thing. Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? Who sucked out the feeling? Where'd you go now that everybody knows that we did a couple shows out there? Look at me, I can write a melody, but I can't expect a soul to care. Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? 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 Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? 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 Who sucked out the
All right, so a couple announcements first. Upcoming here is a Food for Thought event on the 29th, so that's what, a couple weeks from now, Wednesday, a couple weeks from now. And it's at 6:30 p.m. here in Avery Hall on the third floor. I do believe that they're serving pizza or something, but don't quote me. Yeah, there we go, Papa John's Pizza. CSAB is the Computing Student Advisory Board. It's a student-run group, kind of like student government. They play an advisory role to the director of the School of Computing and to its faculty as a liaison. So you can go there, you can share your thoughts on the program, the facilities, and everything like that in an anonymous way, and then they'll share it with the faculty at the student advisory panel, which is probably the week after that. Also probably pizza there, but it'll be during the day, and then the faculty will actually be there at that one. But the faculty won't be at this one. You'll be talking to your student representatives. So plan on being there if you're interested in providing feedback on any of the degree programs or the facilities or whatever. Second is I'm wanting to plug, I'm the faculty advisor for Corn Hacks. Corn Hacks is our annual hackathon, and usually it's in the spring, like right as you come back from in the spring semester. But this year it is in early November. So right now is the time that you should be thinking about signing up for this. It's not required or anything. It's a hackathon event. I think it's 24 hours. Yeah, 24 hour that you come up with an idea. Maybe it fits the theme, maybe it doesn't. You and your team will then program the idea and then present it, and you can win prizes. Pretty good prizes in the last couple of years, mostly Legos. So some cool Lego sets that are available. Even if you don't win, even if you don't plan on winning or going for the prizes, it's still a fun event. You can get some food, you can hang out, and it gives you an opportunity to learn something new over 24 hours. So if you're interested in that, make sure that you're going to unlcornhacks.com. You don't need to go to the home address there, but that's where it'll take you. And then you can go ahead and sign up for it. Where is the sign up? register right there, right? Or you can help organize it if you want. But otherwise, registration is free. All you have to do is sign up for a team of, I think you can do it alone, but a team of up to 4 people. Right? So that's our annual hackathon event. Next announcement is, like many of you have already experienced, CodePost is not, its back end, its front end is working fine, but its back end is not working great. So make sure that you point your web browser over here to the CampusWire, because we have an alternative for the time being. Hopefully they get it fixed. I've been in contact with, I don't know if there is any live support anymore, but I've been in contact with at least one of the people that has been involved with it. And hopefully it'll get resolved. If it doesn't get resolved, it's probably not going to get resolved today. But if it doesn't get resolved, then this is what we'll be doing going forward. This is our old hand-in system. So you point your browser to cseapps.unl.edu/handin. Once you're there, if you've got multiple courses like I do, then you would go to the appropriate one. Otherwise, it'll take you there immediately. Hack 6 is the only one I've set up so far, but I will be setting up for lab tomorrow in this as well, anticipating that CodePost will still not be up. But you go to that hack and you drag and drop your files, or you just click here, and then it'll open up a dialog that you can hand stuff in. But once you've handed it in, right, then you go to the secondary system, and I'm not going to copy that URL right there. Instead, make sure that you're going to this URL here. By the way, to log into both of these, you still use your Canvas credentials. The same username, same password as you would to get into Canvas. Once you've handed it in, you can come over here, and then there's a drop-down selector for what you want to grade. There will be more things by the end of the day here, and then you just hit Grade Me. Right? Sometimes it errors out because I've been logged in for a long time, so it logged me out here. Let me go ahead and refresh it. All right, there we go. And grade me. Right. There you go. And it shows you what it's not going to be as automated as CodePost. In other words, it's not going to say you've lost 5 out of 15 points for this thing or that thing or whatever. Instead, it's going to simply run the test cases, the CMOCA test cases that you handed in. So remember that there needs to be 27 because you need to do 3 of your own. And so this is just what we had from the handout. This is 24 test cases here, so obviously I'm going to lose points because I didn't do the entire work. But you'll see that a report exactly as you would see it if you ran it on your own computer. All right. Other things, and I don't have them set up right now, but other things will be like input-output. So there'll be the expected output over here, and then your output would be over here, and then you would visually inspect and see does it match. All right. So that's why it's less automated than CodePost, because it's a little bit more flexible. We allow anything. We allow any formatting or whatever. Unfortunately, if CodePost remains down, grades will be put manually immediately into Canvas, including all of our comments. So you won't see the line-by-line comments that you would see in CodePost if it remains down for any much longer here. All right. Any questions on how to do? Oh, and then also, if you take a look here, what was the due date? The due date was extended till tomorrow midnight, but hopefully most of you are already done with it. But it was extended only because of this issue here. Yeah.
If we submit it into CodePost, could we resubmit?
Yes, please, so that it's, just to make sure. When the grader goes through manually that's assigned to you, they'll check here, and then the instructions I'll give them is to check CodePost as well. Anything that made it in there, I think, as of Friday evening, or maybe it was Saturday evening, which should still be good. But go ahead and rehand it in anyway. Any other questions? No? Okay. So this was available at the top pinned post on CampusWire. Right. Go ahead and get rid of those. All right, so what I want to do with the remainder of our time today, remember that what we're going to do is finish up Arrays today, and then on Wednesday and Thursday we'll be doing tooling. So I will introduce you to GDB, which is a debugger. It's a debugging tool. And then also Valgrind, which is a static analysis tool. So today I just pulled out my textbook here, and we'll do as many exercises as we're interested in. And these are array exercises here. Yeah, this one's good. So write a function that takes 2 arrays, A and B, and creates and returns a new array that is the concatenation of the two. That is, the new array will contain all the elements in A, followed by all the elements in B. So if there are 5 elements originally in A and 5 elements originally in B, then the new array should be of size 10. Okay? And it contains everything from A and B. I also added this. This is from lab here. I added this array, random array generator. You can see it working here if you want to. But basically, you run it and it'll fill it up with a bunch of random integers between 0 and 999. You run it again, different, right? But you tell it what size you want and it'll give you a random array. So you don't have to manually create one every single time. Right? So what I'm going to do is I'm going to anticipate that we want to test this. I'll create a random array A and a random array B here, maybe of a different size. So I'll say M instead, and that there are 5 things there. And I'll call it BRR instead, BRR, right? Okay. And ultimately what I want to do is I want to combine these two things. Come on, type, and BRR, right? Now if I just ran this, of course, you would see A and B here. Those are going to be my inputs. I want to combine them so that I get another array called, say, maybe SIR, right? So int CRR, all right, is equal to, now I want to combine the arrays, right? And then print them out. Of course, I need to write the function to do that. So let's come up here and what should we call this function that takes this array and simply just appends this array to the end and gives you that new array? In the handout, we call it the concatenation. So, I don't know, concatenate, right? The two arrays. So I'm going to give you an array A and array B, right? Those are going to be my 2 inputs. And I'm going to return an array C, right? But that's obviously not correct C. How do we return an array? Int star, right? Of integers, right? It's going to be a pointer. All right, how do I take an array? Well, am I going to be making any changes to it? No, so I will make it const, right? Array, the A, I'll just call it A in this case, int M, and const array B. Sorry, I lost my C there. All right, and I also need to tell it how big it is, int N and M, there we go. Now let's document what this actually does. So returns a new array that is the concatenation of the 2 given arrays of sizes N and M respectively. All right. So those 2 are concatenated. How big should the resulting array be? The resulting array is, in the example that we just did, it would be 15 because 10 plus 5. But if we're going to keep it general here, N and M, N plus M. All right. So unlike the get positives that we did last week, which we still have to write documentation for, right? There we didn't know how many positives were in there. So the function had to communicate back to the calling function how big the result of the array was in this pass by reference variable here. We don't have to do that here because by design, if you give me N and M, you're telling me how big the original arrays are. You have N and M. You can add them together yourself, right? And so that's that's the design that we'll take here. We will concatenate ARR, which is of size N, and BRR, which is of size M, and we know how big the resulting array should be. Print array CRR. How big should it be? N plus M. Right? We know that, right? We have enough information that we can figure that out ourselves. All right. So let's go ahead and write this function now. Okay. What's the very first thing I should do? Error handling. If A is null, or if N is negative, or if, what else could be null here? B is null, or M is negative, then we'll return 1, an error code? Nope. What's our return type here? Int star. It's a pointer. What is the only pointer that indicates an error occurred? Null. Okay, null. Yep. All right. Otherwise, I need to create a brand new array of size N plus M. So int star, I'll call it result. Right? is equal to int star, that's my typecast there, Malik. Right? How big should it be? Size of int, and how many are there going to be? N plus m. Is that good math? No, plus comes after the multiplication, so what should I have done there? Parentheses. Okay. And don't forget your return statement there. Result. There we go. All right. Now, is that enough? I haven't copied anything over. So first of all, I need to copy elements from A over, and then copy elements from B over to result. Right? So copying elements of A should be pretty straightforward, right? For int I equals 0, this is our idiomatic for loop. I is less than n, I plus plus. Right? The result sub 0, or result sub I, excuse me, is equal to ARR sub I. Right? That's pretty straightforward. We've done that now a couple of times. Okay? But we have to be careful when we're copying over B. What if I just copy pasted this code right here and changed it from N to M and ARR to BRR?
You just overwrite all our hard work.
Exactly. We would have overwritten everything that began at the beginning with those things that are in B. Remember that the first 10 things, 0 through 9, that's already been taken care of. I now need to take care of 10 through 14 in my example. So should I be starting I at 0? No, where should I be starting it? N. Right. While it's less than M, well, it's not. If M is 5 and I've started this out at 10 already, 10 and M is 5, as in my example, is that even going to execute? Nope. All right, so I do agree with starting it at N, but where should I go up to and not include? N plus M. Or, let's go in order. N comes before M in the alphabet, right? There we go. NM. Okay. Now here again you have to be careful because I and I. Where is I going to start out initially? At 9 in our example where we've got 10 and 5, right? But then B, remember, is of size 5. Is there an index of value 9? Nope. So this is correct over here on the left-hand side. Oops. But what about the right-hand side? I want to start it at 0. Then I want it to become 1. Then I want it to become 2. Right? With respect to I, though, what is that? I minus n would on the first iteration, what would that be? 0. On the second iteration, what would it be? It'd be n plus 1 minus n, so 1, right? Et cetera, et cetera. Right? So by changing that index there, I'm copying it over here, and then I'm copying over there. Right? Let's actually see this in action. Let's go ahead and use Python Tutor here. Normally, I would whiteboard this, right? You would go up to a whiteboard and you'd say, okay, well, on this example, how would it end up working, right? Or you can use Python Tutor here to figure it out. I'll go ahead and put that up there, and then I'll also steal my other main code up here. Unfortunately, I'm not going to be able to use my main code. Instead, I'm going to have to type something out here. All right. There we go. I'm just going to have to create 2 integer arrays here. Int A is equal to, or ARR, is equal to 2, 3, 4, 5, 8, 7, 6. There we go. And that's good enough. How many are in there? 7? All right, 7. All right. And then I need another one, BRR, and I'll go with just the first 3 there. 3. All right. And I don't need to print it because this is a visualization. We'll be able to see how this is actually working. Yeah, go ahead.
I think you forgot to change this.
Oh.
Yes.
BRR.
Thank you. Where?
You have 2 ARs.
All right.
Where it says 2, 3, 4, that should be BRR. Not
Thank you. And I forgot all my semicolons. BRR. All right, there we go. And there's also something up here. Results. Result. I don't know if there's... ARR is undeclared. Oh, that's because I changed it to AR. Let's go ARR up here and BRR. I like those. We'll stick with them. All right, fine. We'll go with A and B. A and B. There we go. All right. So let's walk through this. You've already got your ARR and your BRR. Now we're about to call this function. All right, it passes all of the error checks here. We've created a brand new array over here on the heap. Remember that these are on the stack because I just statically declared them as examples here. And we're going to go through that first loop, which is straightforward because all we're doing is copying over everything from ARR. Right? So 2 through 6 right there. Okay. But now again, what happens here is that we need to start our indexing at 0 over here in BRR, and then we need to start it at 7 over here for the actual result. I chose to do that by starting my I here at n, which is going to be, what value is n? 7. So that'll end up starting right here at this index. And then it'll go 7, 8, and 9 for this loop. But it'll also adjust on BRR over here by going down 7, right? So that'll be what? 7 minus 7 gets me 0, and so it copies it over to 7. 8 minus 7 is going to get me 1, and so it copies it over there, right? And then 9 minus 7 is 2. Right? So if you're ever off by 1 or you need to understand how is my indexing working, you can always come over here to this visualization tool. Right? Did it work over here? I think that there was still, I carried over those syntax errors, so I don't know if it worked over here or not. Let's see, A and B. There we go. GCC. There we go. And remember that these are randomized, so it's going to be that one right there, which matches. Looks like it matches to me. And then 671 through 286 is also appended to the end of that. Okay. All right. Let's see. This is another nice one. Write a function that takes an array of numbers a and an element x and returns the multiplicity of x. The multiplicity is the number of times that x appears. So in this case, I think that they're all unique because, of course, it's randomized. But if I had another example, say, let's come up here to the main. If I had another example, say, int prime, or int foo, let's say, is equal to 2, 3, 6, 5, 2, 4, 8, 2, 3, 1, 2. How many times does 2 appear in there? 1, 2, 3, 4. So the function should return 4 if you gave me this array, and how many times does 2 appear? So let's write the prototype for this first. What's my return type here? What should I call it first, I guess? Multiplicity. That's because that's what it is, right? It's the multiplicity of x. Right? So we're going to take an array, which we're not going to change, so I'm going to make it const of size n, but also int x. Okay? So computes the multiplicity, the number of times it appears, multiplicity of x, right? The number of times it appears. So I'm going to go ahead and use that as my return value. You don't always have to design functions with error codes in mind, right? That is a design decision that you make. Of course, if we tell you write this thing and it should return an error code, right? Then we're dictating the design, but you don't necessarily have to. If I did, what would it look like? Well, that would be an error code right there. And then I would actually have to communicate the multiplicity by a pass by reference variable here. Multi or mult. I'll just go mult right there. Although that's kind of confusing. Multiplicity. Now that's even more confusing. Why? Because the name of the function is the same. And this is why it's very common to put in get in front of it. Get the multiplicity, right? Because remember, that functions are usually verbs because they do things. Variables are usually nouns because they are things. Right? So which design do you want to do? This one or the other one? Well, let's just do this one. It'll give us some extra practice on pass by reference variables. Right? All right. Okay. To do error handling. At this point, I think you can probably do it on your own. What would you need to check for? Null, out of bounds. Wouldn't have to check for anything for that, right? Because what if it's 0? Well, that's just asking how many times 0 appears. What if it's 42? Well, that's just asking how many times 42 appears. You'd have to check for what on this one, though? Null. Right? Note the contrast here. When a pointer is accompanied by n or the size, implicitly that's going to be an array. There's more than one thing. But when a pointer is not accompanied by the size, implicitly it's one thing. Right? And then, of course, you'd read the documentation to be sure. But otherwise, error handling, I'll let you do that. Right? Return 0 at the end because no error. Okay? All right. Ideas? Okay. If a sub 0 is equal to n, or x equal to x, I found x. Right? But I didn't find how many times it did. Yeah, okay, so a counter variable. I like that. Count is equal to 0. Remember, if you don't initialize it to 0, what value does it have? Who knows, right? What? A loop, right? For loop, right? Because these are all arrays. You know up front how many times you're gonna go over it. Int I is equal to 0. I is less than n. I plus plus are idiomatic for loop. Now I'm going to move this up here. Right? Okay. And it's no longer 0. It's I. All right. So if the ith element is equal to x, I found it, or if I found x again. What do? Count plus plus. Okay. And then I need to return the count as multiplicity. Right? I'm not even going to bother spelling it correctly because I'm going to retype this. Right? Okay. How do I return a pass by reference variable? Multiplicity equals count star on the left or right? Left-hand side. Okay. Now you could argue, well, wait a second. Why do we even need this second variable here? Why couldn't we have done this? Right? Why couldn't we have dereferenced it, set it equal to 0, and then went and gone like that? That's wrong. There is a order of operations here. The plus plus would actually occur first. So you'd actually be moving over 1 byte, right? So there are 4 bytes here. You'd move over to this second byte, and then you would dereference that, and it would end up doing nothing. So if you really wanted to do this, you would have to remember what the order of operations was and use a parentheses appropriately. I hate doing that. This is why I will usually, yes, it creates another variable, but I only like interacting with pointers once at most, right? And so I'm going to do that. I'm going to keep my own regular old variable here, increment it as many times as need be, and then I will set my pointer variable once, right? Okay. Some people wouldn't argue, wouldn't do it that way, but whatever. Yeah.
Just playing devil's advocate, why couldn't you just do count? You make count in it, and then that'll ultimately be the same number. So why couldn't you just return the count?
That was the original design without error handling here, right? So this design where we're doing it with a pass by reference variable returns a non-zero error code for any error condition. Right? So it's whether or not you design it for error handling or not design it for error handling. And we did it like this for error handling, and I left it in as a to-do for you to do. Right? Otherwise, let's check out main, and let's go ahead and there's foo, and I will ask, what's the multiplicity? Count is equal to multiplicity of foo, and how many things are in there? 4, 8, 11, it looks like. X. Oh, and then I need a count, sorry. How do I pass in count? Because it's a pass by reference variable. Ampersand. Let's make sure that it works. Printf. Count is equal to %d and the line count. Right. So GCC this. Oh, I never did x. Let's put that into a variable. X is equal to 2. That's what I want to count. I misspelled it somewhere. Oh, it's get multiplicity. Oops. Get multiplicity. There we go. All right, so now remember we counted up the number of times that 2 appears as 4, and it looks like it works to me. All right. We, of course, want to test this a little bit more rigorously. What about 3? How many times does 3 appear? Twice? All right, that looks good. How many times does 42 appear? 0. All right, I like that. All right. Okay. All right, let's see. Where was it? Find. There we go. Here's a follow-up. Right. Write a function to compute the mode of an array of numbers. The mode is the most common value that appears in the array. For example, if the array contained 2, 9, 3, 4, 2, 1, 8, 9, 2, the mode is 2. For some reason, I like 2. As it appears more than any other element. The mode may not be unique. Multiple elements could appear the same maximal number of times. So there could be 5 2s and 5 1s and 5 8s, right? Your function should simply return a mode. It doesn't matter which mode, okay? So let's do that now, okay? I'm not going to do error handling. I'll just say get mode. Right? Const int star a, int n, and int x. So actually, do I need x anymore? No. I just want to know what the mode is. Returns a mode of the given array of n elements. That is the most common element. So you've probably done elementary statistics before. You've probably all seen the mode before, yes? Yeah, okay. You can have multi-modes, right, where there are several modes. That's why it's not unique, okay? All right, let's do that. What would the mode be in our example right here? Int m is equal to get mode, right, of foo and how big was it? 11. Right. Printf mode is equal to %d and the line m. What was the mode again? What's the most common element there? I think it's 2, isn't it? How do we know that? Well, 2 appears 4 times. All right, let's figure it out. Let's whiteboard it on this whiteboard right here. How would we figure this out as humans? All right, 2. That appears 1, 2, 3, 4 times. I'm going to go through and I'm going to count up the number of times it appears. 3. That appears 1, 2 times. Is that more than 4? Nope. 6. That appears once. That's not more than 4. 5. That appears once, not more than 4. 2. We've already seen that. 4. That appears once. 8 appears once. 2 appears 4 times. We've already seen 3 that appears twice, and 1 appears once. Right? So in other words, I was keeping on track on one hand here how many times it appeared and what it was. In this case, 2. Okay. All right. Let's go ahead and implement this. As with all good developers, I do not like to write more code than I have to. Is there a way that we could leverage some of the code that we've already written, that we just wrote, in order to figure this out? Remember that 2 appears 4 times. 1 appears once. 3 appears, I think it was twice, right? Et cetera, et cetera. Is there a way that we could reuse this code to leverage that code in order to find the mode? Okay. So let's go ahead and create a int mode, right? And int mode count. Right? I'll go ahead and set that equal to 0. What we initialize the mode to, it doesn't really matter. I'll go ahead and just start it out with the first element here, because there's got to be some mode. And of course, I'm going to put in a to-do error handling. Right? Okay. So I'm going to first assume that the first one is my mode, unless I find something else. And I'm going to assume that it appears 0 times because I'm going to go through now and count how many times it appears. But guess what? I've already got a function to do that. Right? So, get multiplicity of in a, n, and mode. Sorry, there should have been an equal sign there. Right? And then the multiple count, right? Okay. So I'm going to have a temporary variable there too, int count. Okay. And I need to pass that by reference. Then I can ask if the count is greater than the mode count so far, then I found something that is more common. Right? I can update the mode to be whatever the value is, right? Whatever, right? And then the mode count, I can update that to be the count. Okay. This is obviously just for one of them, right? If it were for the first one, what would it look like? I want to know how many times the first one appears in this array of size n, and and I'm going to pass that by reference. And if that's greater than the mode count so far, then the mode count will be a sub 0. Right? That's doing it for the first one. What would it look like doing it for the second one? Change the zeros to ones. Change that to 1. Right? Okay. What would it look like for the third one, the fourth one, the fifth one? Right? So you see this kind of strategy. Do it for one and then generalize it for each one. Right? All I'm going to do is change this to I and surround it with our regular old idiomatic for loop there. For int I equals 0, I is less than ni plus plus. This is really inefficient, by the way, but that's intentionally so because we're going to explore that issue later on in the semester. Right? Okay. And then ultimately what I'm going to return is the mode. Okay. Now remember, 2 was our mode. Do I have all the code done? Oops. Int m. Oh, I already did m. Sorry. I should have called it mode. Where is 82? In main? All right, just search for main. There we go. 82. There we go. Mode and mode. There. I've already used m. That's why. All right. There. That was from the previous exercise. That's not this exercise. The mode is 2. Let's see if it works if we create a different mode. 3, 3, 3. Now 3 appears 5 times, right? And I need to add 3 in there, so that's going to be 14 and 14. There you go. So it should come back with 3 now instead as the mode. Right? Good question here. What if 2 appears 4 times and 3 appears 4 times? Which one will it actually find? 3 or 2? Let's find out. In this case, 2. Why? Yeah, 3. I agree that 3 occurs later, but remember that how are we breaking ties? Right? Are we breaking ties or nope? The first one we find with the maximum number of count, that's the one that we find, right? Or that's the one that gets reported. Okay. If we wanted to, we could change this, and now what would it be? Now it would be the last one that we find, and it's going to end up being 3 in this case. Right? I don't want to break ties. I'll just leave it like that. Right? Do this again, but instead of finding a mode, what if I asked you to find all the modes? Right? Then what would you be returning? You'd be returning an array of modes. Right? We won't go that far today, but you could do that as an extra exercise if you wanted to. Let's see. I'm going to come back up here and let's see. Get rid of all the print statements here. In fact, I'll get rid of all of this stuff right here. Right. There we go. And get rid of this. There we go. And let's go ahead and create a new foo. Int star foo is equal to random array of, say, n elements. And I'm going to set int n equal to 10. Okay? I'll get that random array, and I'll print it out for now. Print array of foo and n. Okay? And then foo and of size n. There we go. Right. Now, more than likely, all of them are going to be unique, so it's just going to report the first one. Right? That's because we're choosing random integers from 0 to 999, but we're only doing 10 of them. So with a high probability, they're all going to be unique. Right? I could run this 100 times, and I would probably not find anything that diverges from that. But if I made it really, really large, say 10,000. Now the likelihood of copies or duplicates is very high. I no longer want to print it though, right? Instead, I will run it. There we go. Oof. What happened? I thought computers were fast. Okay, let's kill this. Oh, there, it finally went. Let me kick this down to only 1,000, right? Computers are fast, right? Very fast. Right? Go up to 10,000. What was it before, 100,000? Okay, 100,000. All right, did you notice that it was just slightly slower? Right? There was like just a momentary hiccup there. But if I go up to 100,000, now it becomes very, very, very noticeable. Right? What was that? How many seconds was that? Here, I'll kill it. Time, A dot out. We can ask the computer to time it for us, and it'll come back with a report here of how many seconds it took, how much CPU time it took. Right? There we go. So in real time is like the wall clock time, right? Like how many seconds in reality have passed. User time, that's how much actual CPU time it was taken. The system time was like it put our stuff to sleep because it was taking so long, and then it woke it back up because it had to do other things. Right? That's what that's referring to. So it doesn't matter. It's system time is negligible. It took like 12 seconds or almost. What if I went up by another order of magnitude? And now let's go back down to 10,000. And let's do this again, but let's time it because that was really quick, but it was a little bit noticeable, right? It was 0.123 seconds. Here we went up to 12 seconds, right? What's a multiplier there? 0.12, what is it? 0.12 seconds, and then 12 seconds. We'll just round it up. That's 100 times slower, right? So let's go up to 100,000. GCC this. And now remember that 10,000 took 12 seconds. Predict, if that multiplier stays, how long would this take? 12 seconds times 100 is what? I can't do that. 1,200 seconds, 2 minutes. So that's 20 minutes there. Right? I'll ask you, is 100 that's a million, sorry. Is a million integers big? That fits in our stack space, right? That's less than 4 megabytes. Why would it take 20 minutes for this to compute something on just less than 4 megabytes of data? Yeah, this is terrible. What's it actually doing? Let's follow this. Get mode is running a loop from I0 up to n, right? 1 up to n, 0 up to n minus 1. So how many times is this actually executing here? N times. In other words, 1 million. Right? 1 million times there. 1 million times is nothing. But it's also calling this function right here. Let's jump into that function. That is running a for loop as well, which is running how many times in this case? Also 1 million. Right? So because it's nested inside of a for loop, what do we have? We have a for loop inside of a for loop. It's just being hidden by a function call. How many times total are we doing, say, this operation right here? 1 million squared. 1 million times a million. What do we call those? 1, 1, 2, 3, 1, 2, 3 squared. Right? 1 million times a 1 million, and we call them trillions. Right? 1 trillion operations. Right? That's why it's taking 20 minutes. Right? Yeah, computers are fast. Computers can do millions, billions of operations per second. We call them flops, floating point operations per second. And I don't know how fast this is. Who knows? But you can have usually laptops and desktop computers are measured in gigaflops, and then supercomputers are measured in petaflops. So it's what is it? Megabytes, giga, tera, and then peta, right? So you're talking about terabytes here or teraflops here, right? And that's why it's taking 20 minutes. If you took it over onto HCC computers or something, they would probably be faster, right? Or how many people have been doing their PDC modules? How many people have looked at that yet? All right, that's fine. You have until November, the end of November to do so. I'll send out reminders about it. Yeah.
Where do you find that?
I'll send out another reminder about it, but PDC at UNL. So there it is, right? It walks you through this stuff of here's the visualization demo. For example, if you were to run 10 tasks on one processor and each one of them takes, say, 4 seconds, how long is it going to take? 40 seconds, because 4 seconds per task, right? Let's run it. I don't want to wait here for 40 seconds, but it'll go through. And over here, notice CPU time versus elapsed time. They're equivalent because everything has to run in serial. Let me refresh this. I just want to start over. Now, what if you did parallel computing where I did this, say, on 4 processors, and each one of them took, let's kick this down to 8 processes here so that it's divisible, right? Now, how long will it take? 8 seconds total of actual real elapsed time here, right? So there's 4 processors working all at the same time on each different task, right? Once it gets done, then there. How many seconds actually elapsed this time? 8 in real time. Now processor time, that's still 32 seconds. You're not buying anything as far as processor time because processors still have to run that stuff. Right? So if you were to take this million times a million operations over to the HCC, that's the Holland Computing Center, where they've got clusters of hundreds or thousands of GPU units, right? Then this would be in the blink of an eye. In fact, we could probably put this up several orders of magnitude, and it would be in a blink of an eye, right? But the way that we've done this is wrong, right? There must be a better way of doing this, right? How do we find the mode? What if we were to sort it, right? All those 2s would be now where? All clustered together. All those 3s would be clustered together. All the 4s would be clustered together. Right? Do you have to go through it so many times now? You can just go through it once. Count up the number of 2s. You're done with the 2s. Count up the number of 3s. Count up the number of 4s. Count up the number of 5s. Right? And at the end, at the end, after you've sorted it, you've only gone through it once. Instead of a million times a million, you've only done a million operations instead. Right? All right, so we're going to get into algorithms and algorithm analysis towards the end of the semester. It's still running, by the way. Right? Like I said, 20 minutes. It's going to take 20 minutes there. Right? How long has it actually been? Less than 10? I'll go ahead and kill it. How do I kill it again? It's not an infinite loop here. It's just a really inefficient, bad program. So how do I kill it? Control C. We'll look at tool. Looks like we only ran it for 6 minutes there. So we'll when we come back next time, we'll go ahead and switch modes, and we'll start talking about debugging and GDB.